Continuing with section 7.4, we now look at examples where we have more than one terms or one factors in the denominator. For this type of problems, we need the method of partial fractions. You may recall from Calc 2. You must have heard about partial fractions. Here we will review the method as along we do our problems. So we will consider three cases. First one, non-repeated linear factors. So if in our denominator of the Laplace transform we have linear factors, when each of them is a different factor, we write the transform as a constant over the first factor plus another constant over the second factor plus a third constant over the third factor and so on. So here in this first example, we have the function negative s minus s divided by s plus 1 into s minus 2. So we will write it like this to create the partial fractions. Now, and our goal is to find the a and the b, the constants a and the b. We will multiply by the common denominator. The whole equation will be multiplied by the common denominator, which in this case is the s plus 1, s minus 2 over here. So when I multiply the whole equation by that, I end up getting negative 7 minus s equals a times s minus 2 plus b times s plus 1. Now I have skipped one step here, which you can skip as well. But this is a very important step. This must be written. Then the next step, as I mentioned, that you can skip, where you are multiplying each term by s plus 1 and s minus 2. Now once we have it in this form, let me call it equation 1, we can now find the values of a and b by distributing on the right side and then comparing coefficients. But that will involve solving a system of linear equations, which in this case wouldn't be too bad because we have only two constants, so we will get two equations. But another quick trick is that we assign or pick values of for s and plug them in and find a and b. So what values we pick again depends on how we are looking at the problem. If you pick just any value, then you will end up getting again the set of linear equations. But if we pick some specific values, we can simplify our work. So what are those specific values? We try to pick values such that one time this term becomes 0 and the next time this term becomes 0. So this suggests that we pick s is equal to 2 and s is equal to negative 1. When we pick s is equal to 2, plug in equation 1, we end up getting negative 9 is equal to b into 3 because the first term is 0, which gives us b is equal to negative 3. Now we plug in s is equal to negative 1. Now the second term over here will become 0, and on the left we are getting negative 6 is equal to a into negative 3, which gives me a is equal to 2. Now that we have our constants, we now go and rewrite our Laplace transform using these a and b as partial fractions. So this is what we call it the partial fraction decomposition. But now this helps us write the inverse transform. So the function f of t, which is the inverse Laplace transform or inverse of the Laplace transform. So the inverse transform of 2 over s plus 1 will be 2 times e to the minus t, and the Laplace transform of 3 over s minus 2 will be 3 times e to the 2t. So this is the solution. Next, if we have repeated linear factors in the denominator. So this is the given problem. Now note here, this is slightly different. On the left side, we see a polynomial in S, and we have f of s, which can actually be factored out. So when I factor out the f of s on the left, I end up getting times f factor, which is s minus 1. And on the right hand side, the numerator is 2s plus 5. Now the denominator, s square plus 2s plus 1 is s plus 1 whole squared. So I will write it as s plus 1 whole squared. The next step is to divide by s minus 1 on both sides, or multiply by 1 over s minus 1. So on the left hand side, we are left with f of s, and on the top we have 2s plus 5. At the bottom now, we originally had s plus 1 whole squared, but now we have this factor s minus 1 as well in the denominator. The next step is to write out the partial fraction. So you take our given, or actually the f of s, the expression for f of s, this one, and we will write it like this. So because s plus 1 is a repeated factor, so it will appear as many times as it is repeated. So we see it is repeated twice, so we will have 2 terms in which the denominator will be s plus 1. And we write both of them with a constant on the top. But in one case, the denominator is s plus 1, and in the other one, so in one case we have the denominator expressed as s plus 1, and in the other term we have it s plus 1 whole squared. Now if it was a cube, if it was s plus 1 whole cube, then I would start with s plus 1 whole cube here, and then we will add a term with the denominator s plus 1 whole squared, and then a third term with the denominator s plus 1. So you have to remember that when you have a repeated factor, you will write the fraction as many times as it is repeated, and the denominator will start with the highest power, go down 1 less each time until you arrive at the power of 1. Plus c over s minus 1, which was the extra linear factor there. Now we follow the same technique that we did in the previous example. We multiply by the common denominator, which in this case is now s plus 1 whole squared into s minus 1. So notice we end up getting this equation. So I can again pick values and for s and try to see what our constants come out to be. So the first value I picked is s is equal to 1. Plugging in this equation, let me number it again. It becomes easier to know which equation we are talking about. So let's say this is number 1. So I plug in s is equal to 1 in the equation 1. So on the left hand side, I am getting 2 into 1 plus 5, so 7. Then a into s minus 1 will make it 0. In the same way, the b has a 7 minus 1 in with it, so that will become a 0. So this term becomes 0, this becomes 0. The only term we are left with is the last one here, which is c times 1 plus 1, so 2c. But then there is a square on top, there was a square on top here. So we get 2 squared c, so which gives us 4c. So we have 7 is equal to 4c, or c is equal to 7 over 4. Now we plug s is equal to -1. Now the the term which has c in it, that is going to become 0, and the term with the b is 0. The only thing left will be on the right will be the term with a. So when we plug in -1, the left hand side becomes 3, and a into -2, and the rest of them are 0. So this gives us a is equal to -3 over 2. Now we are left with finding b. So we now pick any value for s and try to see what happens. So the easy thing is to plug in 0 for s, is for easier calculations. The left hand side is 5, and plugging in 0 for s, we get -a. Plugging in 0 for s in the second term, so we get b into -1, so -b, so -a, -b, and plus c into 1, so plus c. Plug in the values that we know. We already calculated c and a, so we plug that in. So we have now 5 is equal to negative of -3/2, which gives me 3/2, minus b, because we don't know the b, so we keep it as it is, plus c. C was 7 over 4. So I have 5 is equal to 3 over 2 minus b plus 7 over 4. I moved the b to the right, or you can say we keep the -b to the right and move all the other stuff to the left. So I kept the -b on the right and moved all the other numbers to the left and took the common denominator, simplified. We got 7 over 4. But remember, that is -b. So b will be then -7 over 4. So I can write the Laplace transform as a over s plus 1 whole square, or -3 over 2 into 1 over s plus 1 whole square, plus b over s plus 1. b is -7 over 4. So we got -7 over 4, 1 over s plus 1. Then plus c, which is 7 over 4 into 1 over s minus 1. So this is the partial fraction decomposition. Now we can write our function f of t, which will be, we call 1 over s square is the Laplace transform of t. So if we had a 1 over s square, I would get -3 over 2t But since we have one, it is s plus 1, so it means if there is a shift, multiply by e to alpha t. So what is alpha here? It's negative 1. So we get negative 3 over 2t e to the minus t. Minus m1 over 4. Again e to the minus t because of that. And then plus m1 over 4 e to the t. So this is our inverse Laplace transform. This is how we do when we have repeated linear factors, and also we saw example when we have just linear factors and none of them repeat. Okay, I'll stop here. Next video and we will discuss what if we have quadratic factors.